So now let's talk about polarization in general, and we're going to touch on what it means for light to be polarized and what it means for light to be unpolarized. Now, in the introductory video, I said that a common application of polarizing filters is sunglasses. So what we're going to be talking about now, though, is another common application for polarizing radiation, which is TV antennas. Now, it depends on where you live, but the VHF, or the very high frequency radiation for that TV antennas pick up, it's going to be polarized either vertically or horizontally. So you probably remember way back in the first lecture when we talked about electromagnetic radiation, that Professor Joe Wolf, he was turning the receiving antenna to try and pick up radiation that was being transmitted from an antenna behind him. And this is a similar sort of thing. Whether your antenna needs to be orientated vertically or horizontally depends upon the orientation or the transmitting equipment that the transmitters are transmitting the signal. So if your antenna needs to be horizontal to pick up the signal, that means that the oscillations of the waves that it's trying to pick up also have to be horizontal, whereas if it's vertical, that means the oscillation of the waves have to be vertical. And when I say waves, of course, when we think about electromagnetic radiation, remember, we have both electric and magnetic fields, and they are oscillating perpendicularly to the direction of travel of the wave. So when we're talking about polarization, we're talking specifically about the electric field, not the magnetic field, just the electric field. So is the electric field oscillating vertically or is it oscillating horizontally? Now, to drive a current in a receiving antenna, the wave has to be coming in at the same orientation. So that's why, for example, if your antenna needs to be vertical to pick up the signal, that means that the electric field has to be oscillating vertically to drive a current through that signal. Through that antenna. Or if it has to be oscillated horizontally, that means that the electric field must be polarized horizontally to drive a current through that antenna. So polarized light, it doesn't just happen naturally from sources. So what I mean by that is, for example, light sources such as light bulbs or the sun and stars, they emit what we call unpolarized light. So for a wave that is traveling in the x direction, remember you've got your electric field that could be oscillating in, say, the y plane, and you've got your magnetic field in the z plane. Now, what we can have though is, if you think about these two waves at right angles, they can be orientated anywhere around the x-axis. So for example, if we're talking specifically about the electric field, it can be orientated. It can be orientated in any way around that x-axis. Same with the magnetic field, so long as they're still right angles to each other. And that's the thing. Even in unpolarized light, the magnetic and the electric fields for that ray of light are still always going to be perpendicular. They're just going to be rotating around the x-axis. So when you're looking at these rays coming at you, it's going to essentially be orientated in any direction. So what we say is, the way that we can draw it is, if a wave is traveling along the x-axis, for example, we'll have the x-axis coming out at the page towards us, or the x-axis will run in and out of the page. The y-axis will be vertical and the z-axis will be horizontal, or just perpendicular to it. So what we can say is that, you know, the electric field component, or the electric field vector, can be orientated at any angle to the y-axis. So it's just going to be rotating around the x-axis like we just said. So we're going to have, for unpolarized light, these are all going to be, we're going to have basically, essentially, even amounts of the electric field components orientated on either side. So a quick way of drawing it, instead of just drawing an array of arrows going around in a circle, the way that we quickly draw unpolarized light is by just doing our axes y and z, and we just draw an arrow up and down the positive y-axis and an arrow positive and negative along the z-axis. So if we just draw a cross with our arrows representing vectors, that's a quick way of drawing unpolarized light. So remember, if we draw the unpolarized light in this way, we're not drawing the magnetic component. So we have Z and Y, but remember, the magnetic component is still at 90 degrees or perpendicular to the electric field. Now the ray is coming out of the page here. So we're just drawing the electric field component though. So really, the electric field could be oscillating in the y direction, up and down the y-axis, or along the z-axis. So what we've essentially done is we have our unpolarized light with the electric field could be orientated in any way along the around the x-axis, at any point on the y or z-axis, and we've basically collapsed our unpolarized light into, for each vector, it's the superposition, of the vertical component and the horizontal component. So that's why we draw this cross like this. What we're basically saying is each vector, regardless of its orientation, is going to be the superposition of a horizontal and a vertical component.